We've learned that an atom consists of a nucleus, which contains protons and neutrons. And that nucleus is small and dense compared to the rest of the atom, which consists of the electron cloud. And remember that electrons are negatively charged, and protons are positively charged. And opposites attract. So the reason why the electrons don't just kind of collapse onto the nucleus is because they have momentum. They're actually moving around in the electron cloud. And those electrons are only allowed to move in certain areas around the nucleus. And it's the arrangement of those electrons that dictates the way the atom is going to react. The arrangement of the electrons around the nucleus of an atom is known as its electron configuration. When atoms are in their ground state, their lowest energy state, the atom's electrons can only reside in certain places. We call these orbitals. And these orbitals reside in shells or energy levels. And those orbitals have different shapes. S orbitals are spherical. P orbitals have 2 lobes. They're more like a dumbbell shape. D orbitals, for the most part, have 4 lobes and take the shape somewhat like a 4-leaf clover. And the F orbital starts to get even more complex in shape. And any orbital will hold 2 electrons, and they must have opposite spin. Here's a periodic table that's broken up into the 4 different blocks, S, P, D, and F. And also you'll notice that we have designations here across each row. So each row on the periodic table is going to represent a new shell or energy level. So this is going to be the first energy level or first shell, second energy level or second shell, and so forth. Now let's talk about these blocks or sublevels. The S block represents the S orbital. And S orbitals are spherical. In a given energy level, there will be 1 S orbital. And it can hold 2 electrons at the most. In the P block, we find the P orbitals. And remember, they're the ones that are kind of dumbbell shaped. And in any given energy level, you would find 3 P orbitals. In the D block, we have the corresponding D orbitals, and there are 5 in a given energy level. And finally, in the F block, we have the corresponding F orbitals, and there are 7 of them. And so, if you looked at an atom with its first energy level with S orbitals, and its second energy level with S orbitals and P orbitals, and then a little further out, a third energy level with S orbitals and P orbitals, and actually these D orbitals, we'll talk about that later, and then a 4th energy level with S, P, and D orbitals, and so forth, it would look something like this. Here's the nucleus. Here's the first energy level with that 1 S orbital. A little bit further away from the nucleus, we have the second energy level, and there's a 2s spherical orbital, and the 2 P's. Here's 1, 2, and 3, kind of dumbbell-shaped 3 P orbitals. Elements that live on the 3rd energy level of the periodic table then are going to be even bigger, and they're going to have a 3s orbital and 3 P orbitals. And the electrons always fill up these lower energy levels first. In other words, you would never find electrons out here in the third energy level if there was space for them to be residing somewhere up here in the first energy level. At least not when they're in their ground state, their low energy state. Now check this out. In the second energy level, we have an s orbital, and it can hold 2 electrons. And in the s sublevel, you have 1, 2 elements. In the p block, we have 1, 2, 3 orbitals. Each one can hold 2 electrons for a total of 6 electrons in the p sublevel. And look, there are 1, 2, 3, 4, 5, 6 elements residing in any energy level in the p block. In the d block, we have 1, 2, 3, 4, 5 d orbitals in any given energy level. That means that an energy level can hold 10 electrons, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements in any energy level in the d block. And of course, with the f block here, we have 7 orbitals. Each one can hold 2 electrons for a total of 14 electrons in an energy level. And if you count these across, you'll find there are 14 blocks or elements corresponding to each f sublevel. So now we're ready to learn how to write electron configurations. And electron configurations are important because they, first of all, tell us where an atom's electrons reside when they're in their ground state or when they become ions. And secondly, they help us to identify how atoms are going to bond in chemical reactions. Let's start out with hydrogen. Hydrogen is right here on the periodic table. It's in the first energy level. So we'll start with its symbol H, and since it's in the first energy level, I'm writing a 1. And since it's in the S sublevel, I'm going to write an S. And since hydrogen has 1 electron, I'm going to indicate that on my electron configuration like this. So then hydrogen's electron configuration, since in the first energy level and the S sublevel, and it has 1 electron, is 1s1. And then a hydrogen atom, of course, would have just 1 proton here in the nucleus and 1 electron right there. That's all there would be to a hydrogen atom. Here's helium. Helium's also in the first energy level, and it's actually considered part of the 1s because helium has 2 protons and 2 electrons. So consider 2 protons in the nucleus and 2 electrons that will both fit into that 1s orbital. Because remember, any orbital can hold 2 electrons as long as they have opposite spin. So helium's electron configuration then, first we'll write its symbol, then we write the energy level, and then we write the sublevel, in this case S. Then we write the number of electrons that are residing in that orbital. For helium, it's going to be 2. Helium has 2 protons, 2 electrons. They're both able to fit in that 1s orbital. And so helium's electron configuration then would be 1s2. If we move to the next element on the periodic table, we'll find lithium. Its atomic number is 3, and it has a second energy level or second shell. And since its atomic number is 3, that means it has 3 protons in the nucleus and also 3 electrons. And so, because these electrons are going to fill the lowest energy level orbitals first, we're going to find lithium is going to fill like this. The lowest energy orbital, the 1s orbital, can hold 2 electrons. So I'm going to put 1 here and 1 here. Now that orbital's full. My third electron then for lithium is going to go into the next lowest energy orbital, which would be the 2s orbital. So it would be someplace within that orbital. So then, lithium's electron configuration is going to be 1s2, because the 1s orbital has 2 electrons in it, and then 2s1. And so lithium's total number of electrons, then 3, is represented as such. The first 2 in the 1s orbital, the last one goes into the 2s orbital. Our next element would be, next to lithium, would be beryllium. And so beryllium's atomic number is 4, meaning it has 4 protons and 4 electrons. So it has everything that lithium has with 1 additional proton and 1 additional electron. And so its 4 electrons are going to fill just like lithium's did. The first 2 are going to go into the 1s orbital. The next 2 are going to go into that 2s orbital. So I'll show that second one. Oh, I'll put it right there. So then beryllium's electron configuration would be 1s2. The first 2 electrons are in the 1s orbital. 2s2 for the 2 electrons that are in the 2s orbital. And beryllium has 2 plus 2 is 4 electrons. Atomic number 5 is boron. Now boron is in the second energy level, but it's in the p sublevel. So since it has 5 electrons, it's going to fill the same way all the ones that came before it did, except it's going to have 1 more electron than beryllium did. So boron's 5 electrons, the first 2 will go into the 1s. The second 2 will fill up the 2s, and the 5th electron rather is going to go into the 2p's. Look, that's where boron is. So it's going to go into one of these 2p orbitals. So we will place it in the 2p orbital. We'll put it right there. So that's going to make boron's electron configuration 1s2 for this orbital. And then we have our full 2s2 orbital. And our last electron went into that 2p orbital. So we write that as 2p1. And then if you add them all up, 2, 4, 5 electrons for boron. So now that you're getting used to how these electrons fill the lowest energy level orbitals on out, I'll show you a really easy way to write an electron configuration simply by looking at the periodic table and counting across. And we'll start with the next element, which is right here, carbon. We'll count across like this. Starting with the first energy level, we're going to go 1s2, 2s, 2, 2p, 2. Let's try that again. So carbon is 1s, 2, 2s, 1, 2, 2p, 1, 2. And I could add that last electron to another p orbital. Oh, how about there? Next we have nitrogen. Nitrogen's atomic number is 7, so it's got 7 protons and 7 electrons, and they're going to fill like this. 1s2, 2s2, 2p, 1, 2, 3. That's 1s2, 2s2, 2p3. And oxygen's electron configuration for its 8 electrons would be 1s2, 2s2, 2p, 1, 2, 3, 4. 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and we would need 4 electrons in those 4p orbitals. So let's say we had 1, 2, let's put 3, and 4. And finally, we'll take a look at sodium. Sodium has a third shell or third energy level. And sodium's atomic number, 11, tells us that it has 11 electrons. And so it's going to fill all of the orbitals just the way all of the elements ahead of it did. And it's going to have the electron configuration of 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 3s1. There's also a shorthand way of writing electron configurations called noble gas configurations. If we wanted to write the noble gas configuration for lithium here, we would look at the noble gas that came before lithium on the periodic table, which would be helium. And so we would write helium symbol in brackets. This symbolizes the fact that lithium has the core of helium, or it has helium's electron configuration, 1s2, and then its valence of 2s1. To write the shorthand configuration for magnesium, we'd find the noble gas that came before magnesium on the periodic table, and that would be neon. So magnesium has the core of neon and its 2 valence electrons. So we would write that as all of the electrons that neon has plus a 3s2. And that's noble gas configuration. A third way of expressing electron configurations is using orbital or box diagrams, and these come in really handy when we're looking at exactly how atoms are going to bend. Let's look at oxygen. Oxygen's electron configuration would be 1s, 2, 2s2, 2p, 1, 2, 3, 4. 1s2, 2s2, 2p4. Well, for an orbital box diagram, we would draw boxes denoting each orbital. So I'll draw a box for the 1s orbital, and I'll draw a box for the 2s orbital. And then, of course, there are 3 p orbitals, so I'll draw the boxes for the 3 p's like so. Now, the 1s orbital has 2 electrons in it, so I'm going to show them as arrows, one going up and one going down. That signifies that they have opposite spin. And then the 2s orbital has 2 electrons in it, so we'll do the same thing. 1 electron up, 1 arrow down. And in the 2p orbitals, then, we have a total of 4 electrons that are going to fill. And according to Hund's rule, each of those orbitals would get 1 electron before any of them got 2. So I'll fill them like this. 1, 2, 3. Now each of those orbitals has 1 electron in it, and the 4th one will go in like that. And there's the orbital box diagram for an oxygen atom. So here's one for you to try. Write the electron configuration for an atom of fluorine. Pause it here and give it a go. Fluorine's electron configuration would be 1s2, 2s2, 2p, 5. The noble gas configuration would be the core of helium followed by 2s2, 2p5. And the box diagram would look like this. And so I hope this has helped you to understand how to write electron configurations. Next, we'll be taking those configurations and looking at how atoms bond to each other in chemical reactions.